Welcome to The Explainer. Today, we're unpacking an absolutely fascinating chapter, the invisible ocean floating right above our heads. We'll be exploring water in the atmosphere, tracking its incredible journey from an invisible vapor that completely surrounds us all the way to the dramatic weather events we experience every single day. If you've ever wondered how a perfectly clear blue sky can suddenly unleash a torrential downpour, well, you are definitely in the right place. Let's get into it. Here's a quick look at our roadmap for this chapter. We are starting with the invisible water around us, moving from vapor to visible, identifying cloud types, checking out forms of precipitation, breaking down 3 types of rainfall, and finally mapping out global rainfall patterns. Section 1. The invisible water around us. Now, to really grasp how water acts in the atmosphere, we've got to talk about humidity. But, humidity isn't just one simple thing. Think of absolute humidity as the literal physical amount of water vapor trapped in a specific box of air. We measure that in grams per cubic meter. But relative humidity, that's a whole different ballgame because it's entirely dependent on temperature. Imagine the air is like a giant sponge. As the air heats up, that sponge expands and can hold way more water. As it cools down, the sponge shrinks. So relative humidity is really just a percentage of how full that temperature-dependent sponge happens to be at any given moment. And this brings us to the tipping point of our sponge analogy, the dew point. As that air cools down and its capacity to hold moisture shrinks, it eventually hits 100% saturation. At this exact specific temperature, the air simply cannot hold even one more drop of invisible water. The sponge is totally 100% full. When we hit the dew point, that's the magic moment where the invisible gets ready to become visible. Section 2. From vapor to visible. So how does that happen? Well, condensation isn't just some magic trick. It's a strict, step-by-step physical process. Step 1, the air loses heat. Step 2, it hits that dew point where its capacity to hold water completely ceases. But step 3 is where it gets really cool. That excess water vapor needs something physical to grab onto to become liquid. It condenses around microscopic floating particles called hygroscopic condensation nuclei. We're talking about tiny specks of dust, smoke from cities, or even salt kicked up from the oceans. What's really wild is how a tiny shift in the freezing point determines the kind of landscape you wake up to. Both dew and frost happen under the exact same conditions: clear skies, calm air, cold nights. But if the dew point happens to be above the freezing point, the moisture condenses as liquid water droplets, giving you a dewy lawn. If the dew point is exactly at or below the freezing points, the moisture skips the liquid phase entirely. It deposits as minute, beautiful ice crystals. And boom, you have frost. Okay, let's clear up a super common mystery. What actually is fog? Fog is, quite literally, just a cloud resting right on the ground. It forms when a large mass of air suddenly cools and condenses on fine dust particles, dropping our visibility to under a kilometer. And mist? Well, it's basically the exact same phenomenon, but mist limits your visibility a bit less. That's simply because each tiny dust nucleus in mist has a thicker layer of moisture wrapped around it compared to the ones in fog. Section 3. Identifying cloud types. Next time you look up, remember this. Every single cloud falls into one of 4 foundational categories, grouped by height, expanse, density, and opaqueness. High up, you've got cirrus, those feathery white streaks. Mid-level brings cumulus, which is your classic puffy cotton wool. Stratus clouds are those massive, flat blankets that just cover the entire sky. And nimbus, those are the dark, dense, shapeless, low-level clouds that absolutely threaten to ruin your picnic with heavy rain. Take a look at this. Notice those classic horizontal flat bases and the puffy, scattered tops over the landscape? That is a textbook cumulus cloud formation right there. You'll almost always see them existing in patches, scattered here and there across the blue sky. But contrast that with what we see here. See how these lower, heavily layered masses aggressively block the sun? They are extremely dense and opaque to solar rays. These are your classic examples of stratus or nimbus clouds, signaling thick layers of moisture and almost certainly warning us of impending rain. Section 4. Forms of precipitation. So, what happens when those clouds get too heavy and gravity takes over? Well, precipitation isn't just rain. It's a highly dynamic mix that's dictated entirely by the temperature layers the water falls through on its way down to Earth. If it stays warm, you get rain. If it condenses below freezing, those moisture particles form beautiful hexagonal ice crystals, which gives us snow. Sleet happens when liquid rain falls through a sneaky freezing layer of air right near the ground and refreezes. And hail? Hail is crazy. Those are solid chunks of ice formed when strong upward drafts push rain back up into freezing layers over and over again, building concentric layers of ice just like an onion. Section 5. 3 types of rainfall. How air gets forced upward in the first place actually determines the type of rain we experience. First up is orographic, or relief rain. This perfectly explains a huge geographic phenomenon, why one side of a mountain range can be a lush green paradise while the other side is a dry desert. Moist air hits the mountain, is forced up, cools, and dumps all its rain on the windward side. By the time it crosses the peak and descends the leeward side, the air is bone dry, creating what we call a rain shadow. Then we have convectional rain, which is an entirely different beast. This is your classic sudden summer afternoon downpour. The sun heavily heats the ground, the hot air rapidly shoots upward in convection currents, forms towering cumulus clouds, and just dumps heavy rain with thunder and lightning. It hits hard, but it rarely lasts long, making it incredibly common in equatorial regions. Section 6. Global rainfall patterns. Let's zoom out. The distribution of water across the globe is far from random. It follows some pretty strict geographical rules. First, as a general trend, rainfall steadily decreases as you move from the hot equator out towards the freezing poles. Second, coastal areas naturally receive way more rain than deep continental interiors. And third, because they are massive sources of water evaporation, oceans receive significantly more total precipitation than our land masses do. The global extremes here are staggering. Equatorial belts and windward coastal mountain slopes are practically swimming in moisture, soaking up over 200 centimeters a year. Conversely, if you look at the interior rain shadows of continents or high polar latitudes, they are totally starved of moisture, receiving less than 50 centimeters annually. It's a massive difference. So we've unpacked the chapter on this incredible system, from microscopic dust nuclei to global rainfall regimes. Here's my challenge to you. The next time you look up and see dark clouds gathering, or you feel that sudden drop in temperature right before a storm, look at your surroundings. Ask yourself, is this a brief, heavy convectional storm? Am I on the windward side of a mountain getting orographic rain? Apply what we've explored in this explainer today. The invisible ocean above us is constantly telling a story. You just have to know how to read it. Thanks for joining me, and stay curious.